Perfect. Now
That's better? Oh, okay.
much better.
Okay, yep. I can hear that now. So, okay, so yes, let's get to the equivalence of DFAs and regular expressions. So obviously there's two directions to showing two things are equivalent. And let's start with the easier direction. That is, given a regular expression, you can construct a DFA. And instead of constructing a DFA, I'm going to construct an NFA. But we know that deterministic finite state automata are as powerful as non-deterministic finite state automata, so this is OK. So let's start with that. So this is the first part of the proof. Given a regular expression, I'm going to come up with an NFA. So by the way, just feel free to ask questions and interrupt me at any time. Just raise your hand, shout out my name. Just call me Robin. Whatever. Say something if you have questions. OK. So we're going to show that given a regular expression, you can convert this to a non-deterministic finite state automata. So there's really only three things you need to worry about when you're converting a regular expression to an NFA. So you can have really simple regular expressions like the regular expression, let's say, just some constant symbol, say 0. So this is easy to make an NFA for. You just whatever your start state accepts 0 and goes to the accepting state. So this kind of stuff is easy. So if your regular expression is just a 0, or the regular expression is just the empty string, or if your regular expression is empty, like it doesn't accept any strings whatsoever, that's easy to make as well. So these are the easy things to do. And it's kind of straightforward. The more complicated operations that you're allowed in regular expressions are taking the union of two regular expressions. So let's start with that. That's something non-trivial. So you have some regular expression R, which is the union of two regular expressions. Right? And so how do we do this? So let's assume that we have NFAs for both R1 and R2. And from this, we want to construct something for the union of R1 and R2. OK, let me continue that here. So let's say this is a NFA for R1. And this is an NFA for R2. So it has some start state and has a bunch of accepting states. Sure. And maybe this one has 3 accepting states. Maybe that one has 2 accepting states. Doesn't really matter. And what I want to do is I want to construct one NFA that accepts the union of these two languages. So, OK, does anyone have any ideas on how would we do this? So how would we construct one NFA using these two NFAs that accepts either strings in R1 or strings in R2? Yep.
Add a start state at the beginning, free transition to either.
Right. So add a start state with a free transition to both of these. So it's a null transition or an epsilon transition. This is our new start state. That's right. And that's it, right? Yeah, you don't need to do anything more. The accepting states remain the same. And the reason this accepts the union of the two languages is, of course, if the string is in R1, it could have gone here and done this, whatever's here, and reached one of the accept states. If it's in R2, it would have reached here, done whatever, and reached one of these accept states. So this whole thing is an NFA for the regular expression R, which is the union of these two things. OK, so this shows that if you have two regular expressions which you know how to construct NFAs for, you can construct one for the union. There's 2 more operations you can do with regular expressions. You can do the star operation. So how do we do this? So now we have some regular expression for R, and we want to construct a new. We have an NFA for R, and we want to construct an NFA for R star. So how do you do that? You have some start state. You have some accept states. OK. OK, yeah. What do you guys think? How do you create a regular expression for R star? Any guesses? Any guesses? Yeah, go ahead.
The accept states go back to the start state.
So the accept states go back to the start state. Yep, that's good with with null transitions. So, okay, that's good. And does this work? Or, yep.
Additionally, the start state should be your set state as
Right. Okay. So your idea was the start state should be an accept state because we need to accept the empty string. We need to accept epsilon. But the problem is if you make the start state an accept state, the start state could be an intermediate state in this NFA. And you might make other states become accept states. This is not a big problem because. Right. So just add a new start state, which is also an accept state, and make a null transition here. So now this guy really does accept R star. If this box accepts R, this whole NFA over here accepts R star. And lastly, what do we have left? We have the only other thing you can do with regular expressions is you can concatenate them. So you have a regular expression R1, you have another regular expression R2, and you can just keep this here. You can concatenate them in the sense that you can accept strings where the first part is in R1 and the second part is in R2. You can do this here. Okay, and how do we do this? Anyone? So you want to accept strings that are where the first part of the string is in R1, the second part is in R2. Yep. Go ahead.
Could you just link the accept states from R1 to the start state of R2?
Yep, that makes sense. So do this, and then we don't want these guys to be accept states anymore, of course, because otherwise you would accept strings that are just in R1. So get rid of the acceptance here, get rid of the acceptance state here. And now what does this NFA accept? First you have to accept something in R1, then you get to go here, and then you accept something in R2. These guys remain accept states. And that's pretty much it. Let me do this. There's only 3 interesting things you can do with regular expressions: union, star, and concatenation. And using these properties, you can build up an NFA for any regular expression. And maybe let's just see a quick example. I don't know, maybe you have the following regular expression. Something like this. So you break this up into smaller steps. Here, this is 0 concatenated with this guy, concatenated with 1, and this guy is just 0, 1, or 1, 0 starred. So you create a machine for, start with the inside guy, let's say. You want to create a machine for 0, 1, or 1, 0 star. So this is a machine that takes, this is 0, 1, this is 1, 0. We want their union, so you use the union rule over there, which is, you add a new start state, epsilon transitions here, epsilon transitions here. These guys remain accept states. So this accepts 0, 1, or 1, 0. Then we do the star operation. So where's the proof for star? So over there, we add epsilon transitions back to the start state, epsilon transitions back to the start state. Add a new start state, which is also an accepting state. Epsilon transitions this way. So this is now 0, 1, or 1, 0 starred. Now we need to accept a 0 here. So should have left some more room, but this is a state that goes in here, only if a 0, and this is a start state. So that was the concatenation operation. And we need another 1 here, so I'm going to concatenate again. So this is a DFA that accepts 1. We have epsilon transitions this way. This guy is your final state. And you need epsilon transitions to the new guy from all the accepting states of the previous guy. So this was an accepting state, this was an accepting state, and this was an accepting state. So you need an epsilon transition here as well. OK, so this should be a NFA for this regular expression over here. Right, and the way to see that is, so you come in, you have to accept a 0, then you can skip all the way to the front and just accept a 1 and go ahead. So that'll be like ignoring this guy over here. And otherwise, you can loop around here as many times as you want and go through, and that'll be like accepting some number of copies of 0, 1 or 1, 0. OK, yeah, so that's an example of how you do this. Any questions about this example, or just the general process of converting regular expressions to NFAs? No, kind of makes sense. OK, so this was the easier direction of the proof, converting regular expressions to NFAs. Let's do the slightly harder direction, which is, given a DFA, you can convert it into a regular expression. OK, so how do we do this? And the way we're going to do this is we're going to introduce an intermediate machine model, which I'm going to call a generalized non-deterministic finite state automaton. And we're going to convert a DFA to this more general object and this general object back to a regular expression. And this is going to complete this part of the proof. So what is a GNFA? A GNFA is basically, it's an NFA with regular expressions on the edges. So the transitions now are not just symbols from your alphabet, but you're allowed to have just general regular expressions on the arrows. So something like this is your start state, this is another state. But usually in an NFA, you'd have something like 0 or 1 over here. But now you're allowed to have a regular expression like this. And maybe this is another state. And this is 1, 0, or 0, 1. Yeah, something like that. So it's more general than a DFA because now you're allowed to put in not just symbols from your alphabet, but also just full regular expressions on the arrows. But what we're going to show is that you can actually reduce this object to a regular expression. So that's going to complete our proof. Does this generalized non-deterministic finite state automata make sense? So the arrows just have regular expressions, and you can get from here to here either by going through these arcs, and then your string would have to look like 0, 1 star 1, 0, or 0, 1 star 0, 1, or you can go this way, and then your string would have to be 0 star. Any questions about what this GNFA object is? No. OK, and for convenience, we also impose a couple of other things on this object, which is we ask there to be a unique accepting state. So there's only one accepting state. This is not a big deal because you can always add one accepting state, make all the other accepting states point to this guy with no transitions, and just make the other guys not be accepting states. So now you just have one. We also insist that there's no incoming edges to the start state. So the start state must look like this. It must have arrows going out, only no incoming arrows. And the accept state, of course, and the accept state must only have incoming arrows and no outgoing arrows. So we're going to impose these two things. But these things are easy to do. You just add an extra start state, add an extra accept state, and ensure that it has this property. And the other thing we're going to enforce is that, this is a trivial thing, but if you have two arrows going from this guy to this node to this node, say, I don't know, 0, 1 star or 0, you should combine them into only one arrow, like this, because you can combine regular expressions. So there's nothing deep going on here. It's just something we impose on this object just to make life easier. OK, so this is what a generalized non-deterministic finite state automaton is. OK, any questions about that? Just what is this thing? Does this make sense? OK, yeah. So let's say I give you a GNFA with only two states. So I'm going to write that as GNFA2. What does that look like? So it has to have one start state, and it has to have an accept state, as we said. And these guys, the start state can only have outgoing arrows. The accept state can only have incoming arrows. And you can only have one arrow between two pairs of states, as we said. So there's one arrow with some regular expression here. So this is a GNFA with two states. And what language does this express? It expresses exactly the regular language expressed by this regular expression R, right? So if you have a GNFA with just two states, the regular expression for the language this accepts is just R. So there's no work that you need to do. It's just written right over there. So a GNFA with two states is great, because we're trying to convert a general GNFA to a regular expression. But if you know that you have two states, then you're done. Like, your job's over. So what we're going to do is we're going to convert a GNFA with a larger number of states to, say, a GNFA with k states into a generalized NFA with k minus 1 states, right? And if we can show how to do this while preserving the property that, of course, they accept the same languages, not the same language, then you can go from k to k minus 1, and you can keep doing this till you get down to 2. Once you get down to 2, you just read off the regular expression from the arrow, and then you're done. So that's the sketch of the proof. So I just need to show you how you do this step. How do you go from a k-state GNFA to a k minus 1 state GNFA? And the way to do this is, so how do you reduce the number of states? You just, delete one of the nodes, right? Or delete one of the states. Like, that's the obvious way to do it. So let's say this is a part of an NFA. I'm just showing you two states, two arbitrary states, say qi and qj. And this is some state that I'm going to delete. So let me call it q delete. So q del. So there's other states in this NFA, but right now I'm just focusing on these three. And this is the state I want to delete. And what I want to do when I delete this state, of course, you're going to break the NFA. And you want to repair the NFA, the rest of the NFA, so that everything still works out. So let's say, for example, there was some regular expression here, R1. There's some regular expression here, R2, and R3. This guy had a self arrow, R4. OK. OK, let's say this is the thing. And now I want to rip this guy out of the machine and come up with a new transition function between qi and qj that still accepts the same set of languages. So how do you do this? So R1 remains, of course. So R1 is good. You can still reach qj from qi with R1. And what about this guy? So what about the paths that go through to qj from qi? They had to pass through this loop. And the only way to do that is if you first accept R2, then you're here, and you can loop around here as many times as you like. So any number of copies of R4, so that's R4 star, and then R3. That's this. And then, of course, we had this constraint that you want to have a unique arrow. So let's get rid of this, and then let's just do R1 or this guy. So what this does is, for these two states, qi and qj, what I've showed you is that if you delete this guy, this state q del, the languages that the strings that were gone from qi to qj still remain the same. So I haven't changed the functionality of the NFA with respect to these two states. But now you need to do this procedure for every pair of states that's once you delete q del. Yeah. Question? Yes. Yeah. Oh, so in my example, I didn't have any arrows going backwards. But yeah, you're right. So let's say if you had an arrow here, R5, R6. Right. So there's an arrow going this way. And now there's a possibility of going that way, which is you could go this way with R5, R4 star, and R6. So R5, R4 star, R6. And if there was originally some transition like this, maybe with R7, then you'll get another guy over here. Right? So that's how so this is the process of ripping out one state from your GNFA and still preserving the language that the GNFA accepts. Yeah. Does that make sense to people? Yeah, question.
Do you have to account for, like, in QJ, you can go to QDel and then back to QJ? Do you have to account for those what are now self?
Yes. All right. Yes. Once I added this, you have to take care of that as well. So when I say you have to do this procedure for every pair of states, this includes the pair of states being the same guy. So we also have to do this for, now that we added the back loops, we also have to think about things going from QI to QI and things going from QJ to QJ. So how can you go from QI to QI? You can, through this, you can go, well, this way, so it's R2, R4 star, R6. So you're going to have to add a self loop here, R2, R4 star, R6. And over there, same thing. You're going to have to add a self loop for this path where you take R5, R4 star, and R3. That's right. So when I say for every pair of states in the residual NFA, so the NFA that you're left with once you killed this state, for every pair of states, you need to do this procedure and just check that, is there a way I could have gone from this state to this other state through the state I just deleted? And if there was a way to do that, you need to fix this problem because you just deleted that state. And when I say every pair, this includes just the pair being from a state to itself. And so this remedies the situation where you killed one state. And this is in general how you go from a k-state GNFA to a k-1 state GNFA. And you keep repeating this process until you come down to a 2-state GNFA. So this is basically the idea. OK, any other questions about this? Any questions in general about the equivalence of regular languages and finite state automata? Make sense? OK, one nice thing to observe in this proof is what properties of regular languages did we use when we do this proof? So, or what the characteristics of regular expressions that we used are, we used the ability to do the union when we combine two arrows. We needed the ability to do the star. That's when you had self loops here. And we needed to concatenate things, because when you take an edge this way, you take a path from here to here and come here, you need to concatenate two different regular expressions. And these are exactly the properties of regular expressions. Like regular expressions are exactly those things you can get by doing these three operations. As we saw in the other half of the proof, that these were the only complicated things. The other things that regular expressions can do is they can be constants, but that's clear. So, I mean, this proof shows you in both directions that GNFAs are exactly capturing the power of regular expressions. We haven't missed out on any properties. Like that would be bad if you didn't use all the properties of regular expressions, because then something's haywire, or maybe you had too many properties and some of them were not needed or something. So it's nice to observe that we used all three non-trivial properties of regular expressions in this proof. OK. OK, any questions about that? Or nope. All right. OK, maybe before moving on to context-free grammars, here's a question. So say R is a regular expression. And so my question is R complement regular? So what I mean by this is R describes a language, right, over some string, let's say 0, 1 star. So it's over the set of all binary strings. And R complement is the language of all things that are not in R. So it's just the complement of that language. Now, is that language regular? So notice that we did not allow the complementation operation, this bar operation, in our definition of regular expression. So this thing, as I've written, is not a regular expression. But the question is, is this language regular or not? So does anyone have a guess or thoughts or beliefs? Just random ideas, anything? Go ahead. Yeah.
Maybe you could just take all your accept states, make them non-accept states, and take all your non-accept states, make them accept states.
Right. So that's something you can do with the DFA. So that's right. So you started with a regular expression. And so one thing you can do is, following your strategy, take the regular expression, go through this proof. So from the regular expression, go through that proof, construct an NFA. From the NFA, construct a DFA, and then swap all the states that were not accepting, call them accepting states. All the states that were accepting, call them not accepting states. So that's going to complement the language for the DFA. And then from the DFA, you have to come back to a regular language. So, OK, if you just want to show it's regular, then that's fine. But if you wanted to actually construct a regular expression for our complement, you'd have to go through this whole loop of reductions that we just did today. And then you would indeed come up with a regular expression for this language. But that might be pretty complicated, because you went through a whole bunch of reductions. But the answer to this question is yes. If you have a regular expression R, its complement is also regular. That is a regular expression expressing the complement of this language, but it's not easy. You can't just get it out of this somehow. You have to, or at least the only way I know how is to go through this long procedure. And there's some way to show that, something like this is necessary, because this procedure actually blows up the size of your expression. And some blow up in size is necessary. It's something that you can show. Anyway, so this machinery gave us something interesting, that it was not clear a priori that the complement of a regular expression is also something that can be expressed by regular expressions, right? If I just shown this to you before giving this proof, you would probably have no idea of how would you ever construct a regular expression for R complement. But now this proof gives us some payoff that you can do this. This proof also gives us other payoffs, like showing you this way of expressing languages is completely equivalent to this machine model, which is nice. So yeah, question.
So if you have a GNFA, so this GNFA is something that takes a string and then in the end it might end up in the accept state or not.
Right.
So that's how it's a one organization. But how does it read? Like from a node, you have many regular expressions. How do you know which node to go to?
It's non-deterministic. So you just say that this GNFA accepts a string if you can write the string as having gone through this GNFA. So even though there's two arrows coming out here, it's not like a DFA where it needs to make a decision. It's just, you can think of it as making all possible decisions at the same time. And then as long as there's some way to reach an accept state, it's accepted. Or in other words, you can say that at the end of the day, after you look at the string, if there's some way to fit the string so that it looked like these expressions, then it's fine. You accept. So just like in an NFA, you had these. You could have something like this with a zero transition here and a zero transition to another state, and and something so on. And then you might say, where does it go? And well, one way to think of it is it goes everywhere simultaneously. But at the end of the string, if any of the branches, if any of these worlds where you've gone somewhere are at an accept state, then you've accepted.
In the NFA, when you go over one edge, you use up one symbol at a time. But the regular expression.
Yeah, that's true. So when you're at different parts, you could have used up a different number of symbols. But that's okay. It's like saying what are all possible things that can get you from here to here. It's either just 0, or it's 0, 1, or 0, 1 star, and that's fine. Like all you need to do is to show how to get here using some path in this NFA. Like it's okay that the lengths are different. Like it's not easy to visualize this, but if you write down a formal definition with transition functions and so on, you'll see that all you really needed was to be able to express the string in terms of just a concatenation of these regular expressions. So it works out, even though it kind of seems non-intuitive why you're able to accept different lengths of things. Does that somewhat answer your question? Or somewhat? OK. We can talk more after class if you like. OK, let me move on to context-free languages unless there are more questions. Any more questions? Nope. OK. So context-free languages, or context-free grammars. OK, so this ends our section on regular expressions, DFAs, so on. And we can now move on to context-free grammars. OK, so this is a concept that's probably easier to explain with the help of an example. And let's start with this language. The set of all strings such that X is a palindrome. So I think we saw this last week. A palindrome is a string that's the same when you reverse it. And this language is not regular, right? I think Scott proved this last time, right? So you cannot. There's no DFA that accepts this language. And you can show this using the argument that Scott gave last time, or you can use this pumping lemma for regular languages. OK. So let me describe to you the following way of generating strings. It might look like a strange way of doing this, but let's just look at this example. OK, so I have some variable A. It's just a variable. And there are a set of things that I'm allowed to do with this variable. So this variable, you're always allowed to replace it with, you're allowed to make substitutions of the following form. Whenever you see this variable A, you're allowed to replace it with 0A0, or you're allowed to replace it with 1A1, or you can replace it with just one of the constants. A is 0, A is 1. Or just a null string, the empty string. OK, what does this mean? So what I mean by this set of rules is you have to start with A. And so these are 5 rules that are stated for rules of substitution for A. So you start by just writing down A. And now you're allowed to invoke any of these rules and make a substitution. So say I invoke this rule over here, the third rule. And what happens is this is a simple for making a substitution according to these rules. From A, you substitute the A with a 0. And now you're left with a string in your alphabet 0, 1 star. And then that's it. We say that this is the string generated by this sequence of substitutions. So let me do something more complicated. So you start with A. We make a substitution. Let's say we use this rule over here. And now we have 1A, 1. And now this A, again, we can substitute using any of these rules. Maybe we use the first one over here. So the 1 stays. Now the A is going to get replaced by 0, A is 0. So you get 1, 0, A is 0. And this 1 is just here. So now we get that string over there. And now again, maybe I want to use one of these rules. Maybe I use this rule over here. And I get 1, 0. And I'm going to substitute A with a 1 using this rule. And I get, say, this string over here. So this is a sequence of substitutions from this list of substitutions that I was allowed to do. And at the end of the day, I got a string over 0, 1 star. So we're going to say that this string is also a string generated by this set of rules. And so this is a set of rules. And the set of strings it generates is all the strings you can get using this procedure. And this defines a language, right? So the language is the set of all strings that you can get using these rules. And and what do you think this language is? And well, I've kind of written the answer here, so it's not a very interesting question. But this is the language of all palindromes. So this is a palindrome. This is also a palindrome. OK, yeah, why is this happening? And well, one way to view this is as you can view this as building up palindromes using smaller palindromes. So these 3 rules essentially say that the empty string is a palindrome. Well, there's nothing in it. 1 is a palindrome, and 0 is a palindrome. These are the 3 things that we know are palindromes. And then given a palindrome, a way to construct a palindrome is putting by zeros on both sides of the palindrome, or by putting 1 on both sides of the palindrome. This preserves palindromness, palindromicity, whatever the word should be. So what this set of rules is saying that think of all the strings you can construct using only these rules. Like you start with something that is a palindrome, one of these simple ones, and then add zeros on both sides or add 1s on both sides. And what I'm saying is that this set of rules actually captures the language of palindromes. Like you can exactly only express palindromes with this, and you cannot express any other language. So this is a procedure for generating languages. And this kind of procedure is what we call a context-free grammar. So OK, does this example kind of make sense? Like, so more formally, what's happening is you have 3 steps. And you have some steps, which is so once you're given a context-free grammar like this, you're also given a start variable, which is always, by convention, the first variable in your list of rules. So you write down the start variable. So that's what we did. We wrote down the start variable. And then now you're allowed to do substitute any variables that appear using the rules. And you keep doing this, repeat to until no variables remain. OK. So this is the procedure that I was following informally. So I wrote down the start variable, and then I'm allowed to use any set of rules I like, any substitutions from here that I like, only from this list, of course, until all the variables are gone. Like at this point, the variables are not all gone, so that's not a string accepted in the language. That's not even in 0, 1 start. So you have to end up with a string that's in your alphabet. And so you keep applying these rules as many times as you like until you're left with a string that has no more variables in it. And that's a string that's accepted by this grammar. OK, so this object is called a context-free grammar. There are some names for things. Like this is called a start variable. This is called the start variable. There's only one start variable, and traditionally it's always the first variable in your set of rules. These are called substitution rules. These things are called variables. Like in this example, the only variable was a. These guys 0 and 1, they're the alphabet. They're sometimes called terminals because that's when your thing ends. Your computation ends when you're left with a string of only terminals. So it's like the computation is terminated. So that's why they're called terminals. Yeah. Yes. Yeah, you can have more variables. Yeah. So I'm going to give you another example of a more complicated context-free grammar. But maybe you have 5 variables, and a couple of variables appear on the right-hand side of each thing. So only one variable can appear on the left, because this is a rule that's telling you how you substitute a variable. But on the right-hand side, you can have more than one variable appearing. Like this rule could have been 0a, 0a, or it could have been 0a, 0, b, c, d, and for other variables b, c, d that I haven't introduced. I'll get to a more interesting context-free grammar in just a minute. But yeah, this is just a very simple example. And what I wanted to say is that this procedure, where you start with the start variable and then keep making substitutions, this whole thing is called a derivation. And you're said to have derived this string from this context-free grammar. Right. So this context-free grammar, as I explained, accepts only palindromes. Right. Okay. So in this simple case where there's only one kind of variable a, I haven't given you any more a complicated example. Is it kind of clear what kind of strings you're allowed to generate? You're allowed to use these rules as many times as you like and end up with a string that has no variables in it, and that's a string in the language. Okay. Any questions about this? Does this concept make sense? Any confused about something? No. Okay. Let me do another example. Let's move here. Let's say. Okay. So actually, instead of doing another example, let me just define a couple of things more formally. Like, we don't really need to use these formal names too much, but just so you know, as I said, there's usually a couple of things that define a context-free grammar, and there's 4 things. And so it's usually a tuple like this. So this is the set of variables. So in this example, just the set of variables was just, there's only one variable a. This is your alphabet. This was just 0, 1. This is the set of rules. So this was this whole block of rules over here. And this is the start state, which is some variable from the set of variables. So formally, we'll define a context-free grammar like this. I'm just writing this, so this is the terminology we're going to use. Variables, alphabet, set of rules, start state. OK, let me give you another example of a finite state, of a context-free grammar. Let's say you have OK. This is an example of a context-free grammar. So what it says is if you see the variable e, you can replace it with e plus e. So OK, let's again write down what is the set of variables here. There's only one variable e. What is the alphabet? So what are your terminal symbols? It's 0, 1, plus, and x. So these are all terminal symbols as well. You don't substitute them any further. They're not variables. And this is your set of rules, and your start symbol is e. So what kind of strings can you generate using this rule? So, OK, maybe someone give me an example of a kind of string that you can generate using these rules. Maybe let's go that way. Just a very simple example. Sorry? 1 plus 1. OK, that's great. So you can generate 1 plus 1. OK, how do you do that? You start with E. You use the rule E plus E. And then you use this rule for, say, the first E. And you get 1 plus E. Then you use the same rule on the second E. And you get 1 plus 1. OK, yeah, that was easy. OK, similarly, you can get other strings. Maybe you can get 1 plus 1 times 1. You can think about how to do that. I'll show you how to do that in a minute. OK, what about this string? Can you get 1 plus 1? What do you think? Can you get this string, or can you not get this string? No? Right, I see some heads nodding. Right, that's right. You cannot get this string. If you stare at this expression for a while, you'll see that it's not possible to get something like that. Anyway, so this language generates some kind of set of arithmetic expressions. And there's these kinds of expressions are not generated by this language. Some are. So OK, let's take this guy again, and let's do this in. Let's look at how to derive that string over there. So you have E. So maybe I use the rule. Maybe I use the multiplication rule, E times E. Then maybe I substitute the first E with the plus rule, E plus E times E. And then maybe I substitute the first guy with a 1. Then maybe I substitute the second guy with a 1. So 1 plus 1 times E. And then I use the third rule. OK. And this is how I got the string. OK, does this derivation make sense? This is how you get the string. OK, so there's another way of viewing these derivations that's a little more interesting than writing it out like this, because this is kind of annoying and painful, which is you think of it as a tree. So you have some E here. This is your start variable. And then I use this rule, the E times E rule. So you draw a tree and you say E times E. And then this E I expanded using the E plus E rule. So this is E plus E. And then this E I replaced with a 1. This E I also replaced with a 1. And this E I also replaced with a 1. And then given this thing, what you do is just drag these guys down here. So I take this guy down here. You get just move everything to the bottom line, so you get to see the string that you have accepted. You accepted 1 plus 1 times 1. So this is a nicer visual representation of how the derivation was done. We started with E. We first used this rule, then we used that rule, and then this is a string we obtained at the end. So these things are called parse trees, and they're a nice way of showing a visual representation of how you did the derivation. OK. Yeah. OK. Any question about this parse tree? Like, does this concept make sense? All you do is write your start variable at the top. That's the root of the tree. And then you keep applying the rules in this way. And at the end of the day, just for convenience, you write these symbols down at the bottom so you see what's the string you've accepted. You can also see the string you've accepted like this. It's a 1 plus 1 times 1. But it's nicer to write them down at the bottom. So you just see at a glance what you've accepted. OK. Does this notion of a parse tree make sense? You can come up with parse trees for this string over here as well. Maybe I'll do that. I have some space over here. Yeah, so this derivation over here, I can show you a parse tree for that. So we started with the variable a. We use the rule that a can go to 1a1. So 1a1. Then we use the rule that a can be replaced by 0a0, 0a0. And then we use the rule that a can be replaced by a 1. And so the string you accepted is So this is the string you accepted. 10101. So this is a parse tree for that sequence of derivations over there. OK, yeah, so this concept makes sense. It's nothing too deep going on here. It's just a way of representing this derivation. OK, no questions about this, right? OK, that's good. So actually, the reason that context-free grammars, context-free languages were invented is to model natural languages, like English and so on, as opposed to programming languages. And it was actually invented by a linguist, Noam Chomsky, who was a professor here at MIT. And the reason he came up with this was that natural languages have this behavior of context-free languages. And let me give you an example. So, and what I'm going to show you is that an English sentence has some kind of behavior like this. So what is a sentence? So a sentence is something like, a very simple kind of sentence would be, you have some kind of, let's say, I'm going to call it a complex noun. Let me call it a complex noun phrase, a verb phrase, and a complex noun phrase. Okay, so it's like, Jim likes basketball or something. So there's a noun-like object, there's a verb, there's a noun-like object, and then you have some rules of what kind of things are allowed to be complex noun phrases. So I have some example over here. So what you're allowed, for example, is you're just allowed to say a noun phrase, or maybe you're allowed a noun phrase with a prepositional phrase. A prepositional phrase is something like, instead of saying, Jim likes basketball, it's Jim with a hat, or with the hat likes basketball. I don't know. You can modify your noun with a preposition, or Jim on the mountain likes basketball. So, and I haven't introduced this or notation. So let's just look at this thing over here. This is a very cumbersome thing to write, right? If I want to write down my rules like this is kind of annoying. It's nice to just combine all of these into one rule, which is just E can go to E times E, or it can go to E plus E, or it can go to 0, or it can go to 1. So this is a very condensed way of writing down this system of equations. They're completely equivalent, but this is just a nice way of writing it. So, so in English, so you might say that the subject of the sentence could either just be a noun phrase, and maybe we're going to say that a noun phrase is just an article times a noun. So article is, and nouns are like, whatever, boy, girl, and things like this. So you can come up with a set of rules like this to describe simple sentences in the English language that maybe you have to have a noun, you have to have a verb, you have to have a noun, but these nouns and verbs can have more things going on. The verb phrase can be a combination of a verb with some kind of, again, a prepositional phrase that says something like, somehow describes the verb happening and so on. Anyway, I don't want to write down an actual context-free grammar even for a subset of the English language because it's really complicated. And of course, the set of nouns is like, there's like 10,000 words there. But this was some of the idea. This is why linguists came up with this idea. It was to express natural languages. And while this hasn't really worked out that well, natural languages are really complicated. But context-free grammars are really nice to describe programming languages because programming languages really are very, very structured, and you can actually describe them like this. They're nice to describe many kinds of things. HTML, for example, if you've seen an HTML page, source code, that valid HTML programs are also a context-free language. It's a whole bunch of nice things you can express with context-free languages because regular expressions and regular languages are somehow just not powerful enough. So we need a little more power, and then you can express a whole bunch of useful things. So I'll give you another example of something from the English language a little later, but this would be cumbersome to write down a full grammar for. But there's a nice example in the Sipser book where he actually sketches out a whole bunch of things here with a limited vocabulary, obviously not with all words in the English language, that would be crazy, but just with a couple of nouns, couple of verbs, couple of articles, a couple of prepositions, and so on. And you can see that all the sentences you construct are actually meaningful sentences. And it's a nice way to think about context-free grammars. So, OK, so let me ask you guys a question just to see if somehow things are making sense. So let's say our alphabet is AB. And now I have the context-free grammar. S is the start state, the start variable. It's ASB or SS or epsilon. OK, so can anyone describe in words to me what this context-free grammar is expressing? Let's just throw out some ideas and tell me give me some examples of things that the context-free grammar accepts, or what is it trying to do, or what kind of strings can you generate with this? Just throw out an example, throw out an explanation, half-baked idea, random thoughts. Yep, go ahead. Right, kind of looks like open and close parentheses. That's right. So if we think of A as open parentheses and B as closed parentheses, this is saying that if you have an expression, you can replace it with, so I'm just going to replace A and B with open and closed parentheses. So what is it saying? So S gives epsilon means just the empty string is accepted by this language. If a string is accepted by the language, then you can put those two strings right next to each other, and that's also fine. Or you can put parentheses around that string, and that's also fine. So this exactly describes the set of languages that have properly nested parentheses. So things like this is fine, or this is fine, but this is not fine. So this is not in the language because the parentheses are wrong. This is also fine. This is the correct way to nest parentheses. However, I don't know, like this is wrong. And this grammar that I described over here only generates the things that have correctly nested parentheses and does not accept objects like this that are wrong. OK, does that make sense? So why did we build the rules like this? Because this describes what is a valid expression, right? The empty string is a valid expression. If you have two valid expressions, you can put them side by side. That's also a valid way of correctly nesting parentheses. And if you have an expression, you can always put parentheses around that. That's legitimate, of course. And that's it. This is a way to describe this language. Yeah, and incidentally, this language is also not regular. You can prove that. Yeah, OK. Any questions about that? Why is this not regular, or what's going on? What is this language? No, we're good? OK. So I've described context-free languages to you, context-free grammars. Oh, sorry, maybe I didn't define the term context-free language. So a language that is generated by a context-free grammar is a context-free language. OK. Yeah, that's a straightforward definition. So if you can come up with a grammar that expresses a language, then that language is said to be context-free. Just like a regular language is one that can be accepted by DFA. Context-free language is one that is accepted by a context-free grammar. OK, so we can ask some of the basic properties of context-free languages, so these are the same kinds of questions that we asked about regular languages. So for example, closure under union, which means given two context-free languages, L1 and L2, is the union of L1 and L2 also a context-free grammar, or a context-free language? OK, yeah. OK, any guesses or any thoughts on this? Do you think the set of all strings that either are in L1 or in L2 a context-free language or a context-free grammar? Yes, no, I see some. Yeah, go ahead.
You could use those start variables, like you make a new one, and then you can go to either one of the start variables.
Right. That's exactly right. So let's say L1's program looked like this. The grammar looked like this. Say start1 goes to something, and then a whole bunch of rules. I don't know. And this guy had some some other start variable. Now you can create a new thing that just says s goes to either s1 or s2, and then you copy down this set of rules, copy them both down here. And what you've done is you said you start with s, and either you can substitute s1 or you can substitute s2, and then you would just follow one of the derivations of these two guys to get a string that's either an L1 or L2. So this shows you that context-free grammars are indeed closed under unions, which is a nice property. Yeah.
So I guess the concern with this union definition is that while it is clear that if you follow only rules from S1 or only rules from S2, you'll not only stick a language that's accepted as the union, but if you mix them, it's not entirely
Right. So what you should do first, yeah, so that's a good point. So if this has any variables that are the same as variables over there, you should change the names of all the variables. So make sure that none of the variable names here coincide with any of the variable names here. And then what that will ensure is if you make substitutions, if you started with S1, like if your first substitution was S1, you will only have a bunch of variable names that are from this block, and you cannot get any variables from this block. So you will never use a rule from this block. And similarly, if your first substitution was S2, you'll only have variables from this block, and you cannot have variables from this block. So that's a very good point. You need to make sure that your variable names are different. Otherwise, you'll use rules for this guy here, and you'll mix up the two languages, and then you'll probably create strings that are not in the language. Yeah. OK. That's good. OK, here's another question. Is the set of regular languages contained in the set of context-free languages? So we saw an example of a language that was context-free but not regular. For example, this one, or just palindromes. But is context-free languages a superset of regular languages, or are they just like incomparable? Like there are some regular languages that are not context-free and so on. So yeah, do you guys have any thoughts on that? Why is this true? I mean, kind of the way I've set things up, it's kind of seems clear that context-free grammars are a more powerful model of computation. So you should be able to cover regular languages. So it is true. OK, so let me give you an example of how you would do that. So say you have a DFA like this. Q0 goes to, I don't know, it accepts A and goes to Q1. Maybe it accepts B and stays here. Q2 is the accept state. This is a variable C. OK, how do we come up with a context-free grammar to express this? So we're going to come up with one symbol for every state of the finite state machine. So say we have symbol Q0, this variable Q0, which corresponds to this guy over here. So this is a start variable, which corresponds to the fact that you start at the start state over here. This is the start state. And what the substitution rule tells us is you can go from Q0 to, say, Q1, but you have to accept an A before it. So this is a variable Q1 that corresponds to this node over here. Then we have another rule from Q1 which says that from Q1, you can stay at Q1 if you like, but you need to have a B up front. Or you can go to Q2 if you like, but you need to get a C up front. And Q2, which is the accept state, just goes to the null string. So this is like we terminate. So if you stare at this context-free grammar long enough, you'll kind of see that this exactly accepts the strings accepted by that DFA over there and no more. That shows you that regular languages are part of context-free, are a part of context-free languages. OK. And OK, that's probably, OK, maybe here's a fun question. What about, so what about complement? So if I have a set of languages, L, that's a context-free language, and if I complement this, a set of all languages that are not set of all strings that are not part of this language, is that a context-free language? Any thoughts on that? Yeah, this is not clear, right? Even for regular languages, we had to go through this whole rigmarole of converting between machines. And here it's not clear, and in fact, it turns out it's not true at all. Like, this is not true. The set of languages is not closed under the complementation operation. So yeah, that's an interesting fact. OK, so here are some interesting properties of context-free languages that you might use that are also useful in constructing context-free languages. So if you have a context-free language for L1 and L2 and you want to get one for the union, you can just use this idea. If you have a regular language, you can always convert that. So here are some properties that help you to construct stuff. OK. OK, maybe let's come back to this example over here. OK. OK, so this is a parse tree for a particular expression in the language. That's not here. Right. So yeah, we had the set of rules somewhere here. It was like E goes to E times E, or E plus E, or 0 or 1. OK. And what we did is we gave a derivation for this string over here. This was this parse tree. And now let me show you a different derivation for the same string. So we first used the times rule, and then we used the plus rule, and then we got this string here. What you can do is reverse the order of using these rules. You can first use the plus rule, so you can get E plus E. And now this E you can expand as E times E. And then this is a 1, this is a 1, this is a 1. And so the string you've accepted is 1 plus times. So this is the same string as this. So you've accepted the same string, but we use two different derivations or two different parse trees. So what's important is the tree structure of these two things is really different, right? It was this tree is slanted this way, this tree is that way. I mean, you can see that these are two different trees. And this is something called ambiguity. And it's not a good thing. So it's called, this is called an ambiguous grammar. So this is a bad thing. We don't want one string to have two different ways of deriving it. This uniqueness will make your life easier in many applications, especially when you're designing compilers to recognize your programming language and so on. You want there to be only one way to get to a string. And that's nice, and that'll make your life easier. But this grammar doesn't have the property. In fact, there's two different ways of getting to the string. OK, does this make sense? That's just the notion of what is an ambiguous grammar. Just if there's any string for which there's two different ways to get to it, or more precisely, if there's two different parse trees for it, then that's an ambiguous grammar. But this ambiguity is a property of the grammar, not of the language. So this same language, the set of all strings that look like that, can be expressed by a different grammar that's not ambiguous. And hopefully I have it written down here. Yep. OK, so this was the grammar we use. Let's not use that. Let's use this other grammar, which says that E equals E plus T, or T. So now I'm inventing more variables. Not equals, gives. T can be T times F, or F. And F can be 0 or 1. OK. So what is the set of rules really doing? So E stands for expression, T stands for term, and F stands for factor. So what it's saying is an expression is a sum of expressions and terms. And so at the end of the day, when you finish doing the substitutions, an expression will just be a sum of terms. A term is a product of factors, and a factor is either 0 or 1. So this is telling you, this is forcing you to derive the string in a particular way, which is that one over there, and this one is not going to be fine. Because you first have to use the plus rule. There's no way to use the product rule and then come back to using the plus rule because you've lost that kind of variable. So this grammar will force you to derive that string in exactly one way, which is E first gives E plus T. And then this T we're going to break up as T times F. Or rather, sorry. What do we want? Yeah, that's exactly what we want. Sorry. We want T times F. This F is going to be a 1. This T is going to be a F, which is also a 1. And this E is going to be a T. T is going to be a F, also going to be a 1. OK, so this is a 1 plus 1 times, this is a 1. So we got 1 plus 1 times 1, which is the same as the string here. But I, in fact, claim that this grammar is not ambiguous. So there's exactly one way of deriving the string, and it's the way that I drew here. So yeah, so what this shows is there are context-free languages for which some grammars are ambiguous, like this one, And some grammars are not ambiguous, like this one. So this is a better grammar if you're writing a compiler and you want to actually use this to do something. You want to use a grammar that's unambiguous. And as we saw, this is a property of the grammar, not of the language itself, because the same language can have two different grammars. One is ambiguous, one is not ambiguous. OK, yeah. Any questions about this concept of ambiguity? No? Nothing? OK. And yeah, all right. So, and this is something that happens in natural languages as well, ambiguity. And somehow the derivation or the parse tree is what gives things meaning. And maybe I won't get into too many examples, but maybe I'll give you one example. So this was an actual newspaper headline from a couple of days ago. OK, so cops kill man with knife. OK, this was a newspaper headline. So what is the ambiguity here? So the ambiguity is it's not clear if this with knife, what is it modifying? Is it modifying, did the man have a knife, or did the cops kill him with a knife? Like, did the cops kill a man with a knife? Man with knife, or did the cops kill a man with a knife? So if you write down a grammar for this, like for the English language, you can see this in Sipser's book with this verbs and nouns and so on. You can construct two different parse trees for this, and then you'll see that the parse tree encodes the meaning. It tells you which, like how this was, like what does this prepositional phrase attach itself to? Is it going with the verb or is it going with the subject? And so that's why linguists still use this context-free grammar structure, because it's a nice way of expressing meaning for sentences. But if you just write down English sentences like this, they're often ambiguous. Like, it's not clear what the sentence means. Yeah, I hope it doesn't mean that they killed him with a knife. Like, I mean, it's kind of brutal. They should just shoot him down, yeah. Right? So, OK. OK. Right. So we talked about context-free grammars. We've talked about it quite a bit. And what we have not talked about so far is, let me erase this portion about regular languages. We've just talked about a way of generating these strings using this grammar, but we haven't talked about any kind of machine model, right? For finite state automata, we had this model, which was the finite state automata, which accepted exactly the regular languages. And it's nice to have a machine model, because then machines are easier to play around with. You can do stuff with them. Proofs are more intuitive. With these grammars, it's not as intuitive to come up with something. And in fact, there is a machine model, which exactly captures context-free languages. And they're called push-down automata, also called PDA, which does not stand for public displays of affection, but it stands for push-down automaton. So, right, it's always nice to come up with a machine model, right? So now you can reason about this object. So what is a push-down automaton? So it's basically, let me just write it in one word. So this is going to be the theme for what a push-down automaton is. It's an NFA with a stack. OK. What's a stack? So a stack is some kind of thing like this. It's literally a stack. This is an empty stack. And you can put stuff into it. You can put symbols into it. So maybe you first put a 0 into it. Maybe you put another 0, put a 1, 0. The feature of the stack is you can only access it in this way. So if you throw stuff onto the stack, you can only pick up the topmost object first. You cannot go in and access this guy over here. So it's like a stack of dishes, right? You stack up the dishes, and the first dish you remove is the last one you put in. It's this one over here. So this is an additional power that we're going to give to our NFA. We're going to allow our NFA to use a stack. And I'll show you exactly what that means. But why is a stack useful? And this stack is of infinite depth. Like, you can push as many things as you want onto it. There's no limit on the length of the stack. And what's nice about this is the fact that now we can recognize languages that are not regular. And one of the examples of a language that was not regular was this guy, right? 0 to the n, 1 to the n. And how does a stack help? The reason a stack helps is what the DFA can do is when it keeps seeing zeros, it can keep pushing zeros onto the stack. Once it starts seeing ones, it can start popping out things from the stack and making sure that they're all zeros. And if the total, at the end of the day, if the stack is empty, and we've kept seeing ones so far, then you accept the string. So that'll exactly accept 0 to the n, 1 to the n. So adding this power of an infinite stack exactly allows you to capture things like this, or well parenthesized brackets. So how do you do these parentheses? You just push these objects onto the stack. When you see the one that's the opposite of this guy, you pull that one out, delete it, and keep doing that. If you see something that's incorrect, then of course you reject. So the stack gives you, intuitively, the stack is giving you exactly the power that you were missing in DFAs. The DFAs, the one thing it didn't have was the ability to store information like this. This is a very limited form of storage. Like, you're not allowed to access random bits that you feel like. But this is still good enough. And this is exactly what you need for to capture context-free grammar. So a push-down automaton is exactly an NFA with a stack. So let me give you an example. This would clear things out. OK, so we need some kind of notation to describe what's happening on the stack and how do you push objects onto the stack, and how do you get objects from the stack. Also sometimes called popping objects from the stack. So let me just describe a DFA for the following language, the 0 to the n, 1 to the n thing that we were just talking about. Sorry, let me describe a push-down automaton for this. So you come in. So the language, the alphabet of the stack doesn't have to be the same as your input alphabet. You can have a bigger alphabet, like some other stack and input are unrelated things. So you can have whatever alphabet you want. So I'm going to have a slightly larger alphabet for my stack, which is going to be the $symbol 0 and 1. And now this is a slightly technical thing, but in our definition of push-down automaton, we're not going to give the machine the ability to test whether we've reached the end of the stack. And this is important because at the end you want to know if you've reached the end. Like, have you exactly got the same number of zeros and ones? But this is not a big deal, because you can always start by putting a special symbol onto the stack. So you can always start your stack by pushing on the $symbol. And then while you're reading it, when you reach the $symbol, you know you've reached the end of the stack. So that's just a simple fix. So you always start with pushing the $symbol onto the stack. And the way we're going to write this is first, so what is the input that you accept? So you don't accept any input at all. Right now, we just want to push something onto the stack. So what we say is you accept the input, empty string. And then our notation is going to be the following. Epsilon goes to $. This is epsilon goes to $. So what this means is you did not accept anything in the input. On the stack, you did not pull anything out of the stack. You just left the stack alone, but you pushed something onto the stack, and you pushed $1 onto the stack. So if your stack was originally empty, after following this, you're going to have the $symbol at the bottom. That's what this is going to do. And here what you want to do is, if you see a 0 on the input, you don't want to read anything from the stack. You just want to push a 0 onto the stack, because now we want to count the number of zeros. And this is going to be an epsilon transition. I'll describe this in a minute. What this is just, nothing's happening really. It's just a null transition to the state over here. And this is a state that does the backwards counting, checking if the total number of zeros is equal to the total number of ones. So now if it sees a 1 in the input, it deletes a 0 from the stack. So that means it reads a 0 from the stack, and it replaces it with nothing. And at the end of the day, if you see the $symbol, then you know you've reached the end of your stack. And you can replace this with anything, it doesn't matter. And this is the accepting state. So maybe this was not very clear. So let me just give an example. Let's just say 0, 0, 1, 1. So let's follow this input. So what's going to happen with the stack is first you start off with just a $symbol of the stack and nothing here. That's when you go from here to here. Then every time you see a 0, you're going to push a 0 onto the stack. So now you're going to have $0 here. At this point, you're going to see $0, 0. OK. And what's happening here? So this is a non-deterministic machine, so it can choose to non-deterministically jump here on this epsilon transition. Goes here. And now it starts popping zeros off. So now there's only $1 left, only $1 left. And finally, it's going to read this and you're going to replace it with the empty stack on this epsilon transition. And this is a way of pictorially representing this intuitive idea that if you had a stack, you can just push the number of, push all the zeros you see onto it, and when you start seeing ones, you start deleting them. Okay, does this kind of make sense as what's happening? So it's exactly an NFA which has access to a stack. Okay, any questions about this so far? Yeah.
Why do you need epsilon transition to epsilon?
Yep, that's a great question. So we don't actually need this. What you could have done is you could have done the one transition, right? Is that what you're proposing? Yeah, that's totally fine. I left it like this because I wanted to go with a more complicated example, but I decided to switch to a simpler example doing this. But you're right. So this is also valid if you have a 1 here and 0 goes to epsilon. This is also legit. So the first time you see a 1, you switch over to this state over here, and now you're in this counting backwards situation, and you come here. Sorry? Oh, I see. Yeah. That's true. You don't get the null string. So, well, maybe I didn't want the null string anyway. Anyway, but yeah, sure, that's right. You don't get the null string, but oh, I see. Huh, okay. Well, maybe that's why I had the epsilon transition over there. Huh, yeah. I guess sometimes I outdo myself. Okay, yeah, I don't know. I came up with this when, yeah. So that's right. Then you wouldn't have accepted the null string, so maybe it's good to have that over there. So one thing you can ask, and okay, in the last 2 minutes, I just wanted, just so you know, we did not get to this part. So I'm going to finish push down automata, and I did not get to this, and so Scott will cover this next time. And he'll show you the existence of a language that's not even a context-free grammar. So it's a mystery. You can think about it if you want. Try to think about why a language wouldn't be expressible by context-free grammar. But there's an interesting thing about push-down automatons, which is that I said a push-down automata is an NFA with a stack. But what if you define a DFA with a stack? So a deterministic machine, but it has this stack, but it's a deterministic machine. So this machine over here, it has a couple of epsilon transitions, but there's some way to define a deterministic machine with a stack that accepts this language. And it's clear that there's basically a deterministic algorithm, right? You just look at all the zeros, you keep pushing them on. When you see a 1, you start popping them off. And then at the end of the day, you've accepted the string 0 to the n, 1 to the n. So this language is indeed acceptable by a deterministic push-down automaton. Let me call it DPDA. But there's the question of, is this equal to just a full-blown PDA, which is an NFA with a stack? So this is like a baby version of the P versus NP question. The P versus NP question is the question for Turing machines. Do polynomial time Turing machines equal non-deterministic polynomial time Turing machines? So we saw this for regular languages. So we saw this question, is NFA equal to DFA? And this was true. NFAs are indeed equal to DFAs. So for this version of this model of the P versus NP question, this very, very baby model of the question, it was true. Non-determinism does not help you at all. Here, it turns out that non-determinism does help you. So in fact, they're not equal. So PDAs are actually stronger than DPDAs. So now you've seen 2 different models of computation, finite state machines and push-down automaton, one where non-determinism helps and one where it doesn't. So this kind of gives you some idea of why the P versus NP question is so difficult, because it's not obvious. Like, you couldn't have guessed this a priori that non-determinism is not going to help you here, but it's going to help you here. Like you might have, after you saw this, you might have guessed that, well, maybe non-determinism just doesn't help. It's just a stupid ability. You can always replace it with determinism, but that's not true. There are some languages that you cannot accept with a push-down automaton, and maybe I won't give you an example of that, but. Or maybe it's actually, I will give you an example. It's easy. It's the palindromes language we just saw. So the palindrome language is an example of something that's a push-down automaton, but not a deterministic push-down automaton. OK, that's the end of the lecture. If you have any questions, please feel free to ask me afterwards. Thanks.
Is there anything special about LIFO? Like, if you gave an NFA a queue instead of a stack, could you recognize the same languages?
No, I think you would recognize a different set of languages.
So it is important somehow that it's a stack.
Yeah, like if you think of this palindromes, for example, you really need to push them out in the same order that they were popped in because you want to match them, from inside out.
Oh, okay.
It's not, but I'm not sure if you would get something more powerful or less powerful.
Yeah, that's Scott.
I'm subbing for Scott.
Cool.